Hello everyone, in this video we're going to cover insertion sort. Now in our previous video we covered bubble sort, which is probably the easiest sorting algorithm for us to understand. This one's not that complicated, but in the future we'll be covering quicksort, which is a better algorithm as far as complexity analysis, but it's also probably one of the harder sorting algorithms to understand or reason about. When you think of insertion sort, imagine an array, and on the left hand side of your array, imagine that you have a partially sorted array, and that partially sorted array on the left hand side is going to grow as you perform your algorithm. So let's jump into an example here. Let's create a random array. So I'm going to just put some elements into this array. I'm going to say we have the numbers 8, 5, 18, 2, and 9, and we want to sort this array using insertion sort. So if we go and look at the very left of our array, so we just look at this single figure or this single number 8, we can actually say that this is sorted. And the reason why we can say that this is sorted is because there's only actually one element that we're looking at. So we know that 8 is sorted. So once we know that this single part of the whole array is sorted, so you can imagine this here as being sorted. I know at the moment it only has one digit, and all the rest of this array is unsorted, or it's potentially unsorted. We haven't checked it yet. We could have an array that's perfectly sorted before we go and perform our sort algorithm, but we don't know this ahead of time. So our next step is to move on to our second digit. So we can see here our second digit is 5. So now we're no longer just looking at 8, but we're looking at 8 and 5. And if we look at 8 and 5, we can check to see if these two numbers are sorted. And they're not, because 8 is greater than 5. So what we want to do is we want to swap these elements. So we want to put 5 here, and we want to have 8 here. And the rest of our array is not going to change. It's just going to be the same way it was before. So it'll have 18, 2, and 9. And I'll just put the square brackets around this to make sure there's no confusion. And now we know that this part of our array is sorted. So our two elements to the left are sorted, but we're still unsure about the rest of our array. So our next step would be to go and check our next element. And our next element is 18. So we want to see, is 18 greater or less than 8? 18 is greater than 8, so this is actually in the right position. And we don't have to compare 18 to 5, because if 18 is greater than the first number that we check here, which is 8, we know that it's going to be greater than all the other elements or all the other numbers to the left of this number, which is 8 in this case. So this is good. We can then move on to our next stage in our algorithm, which is to check our next element to the right. And our next element to the right is 2. So when we compare 2 to 18, we check to see if 2 is greater or less than 18, and we can see that 2 is less than 18. So if 2 is less than 18, we need to swap these elements. So you could imagine our array would look something like this, and I'm just going to draw it out here for you. 5, 8, and now we don't want 18, we want 2. And then we fill in 18, and we finish that off with 9. Now, we haven't fully got a working solution here, or we haven't fully completed this step, because if it's a case that this number here on the right is less than the number on the left, then we switch it. So that's perfect, we've done that. But if we had to switch it, we also need to check this number here that we've just moved and compare it to the element to its left. So in this case, the number 8. So we need to check to see, is 2 greater than 8? And it's not. So it's not in the correct position. So again, we need to swap this again. So we would then have 5, 2, 8 because these two swap, and then we would have 18 and 9. And then imagine if we have 5, 2, 8 here, we also need to check this number 2 with 5 because, again, we've just moved this number. So we need to make sure to compare it to every single element once it has been swapped previously. So again, 2 is less than 5, so we're going to have to rewrite our array to look something like this. We're going to have 2 at the start, then we're going to have 5, then we're going to have 8, now we're going to have 18, and now we're going to have 9. And now we go to our next element, which is 9, and this is our last element. So once we've completed this last element, our array should be sorted. So again, we can check this by comparing 18 to 9. 9 is less than 18, so it's going to have to be swapped. So it'll look like this, 9 and 18. And what we can do now is we can compare 9 to our next number to our left, which is 8. And if our number here, so if 9 is greater than 8, everything's okay, and we can just fill in the rest of the array the way it is. Now, if this number here wasn't 9, let's say this number was 7, which is less than 8, we would then swap 7 with 8, and then we would have to compare 7 just to check to make sure it's in the right position with the number 5 here. But in this example, 9 is greater than 8, so we can just fill in the rest of the array the way it is. And if we just fill in 8, 5, and 2, and we'll wrap that in square brackets to identify it as being an array. And now if we go through all our elements, 2, 5, 8, 9, and 18, we can see that this is now a sorted array. So if you want to know more about the complexity analysis of insertion sort, or you want to know how you'd go about coding up a solution to implement insertion sort, go and check out some of our complexity analysis videos.